Let's get to the next example now, permutations with repetition. Permutations, you remember, that's the playlist example, and with repetition what I mean is that you have a playlist, let's say of these 10 songs, but because you like it so much, yesterday appears twice on your playlist. Well, the thing is now, when you switch the two yesterdays, the playlist is still the same, so you shouldn't count it twice. And that's exactly the topic of permutations with repetition. So the same element occurs several times, and we're nevertheless interested in how many different arrangements are possible. As an example, we'll use the timetable, meaning we have a class that has 3 maths, 2 German, 1 English, and 1 French lesson on Monday. The question is how many different timetables are possible with these lessons. This means in how many orders can the lessons be arranged. For example, you can have first math, then German, French, then math, again math, English, and German. Or you have German, math, French, math, English, German, and so on. Question: how can we find out how many different timetables there are? The idea that we use is the following. We assume that in reality there were 7 different subjects, so we say the math actually is a M1 for, let's say, for algebra, and M2 for geometry, and M3 for functions, whatever you like. So actually we don't have just 3M, 2D, 1E and 1F lesson, but we have the lessons M1, M2, M3, D1, D2, E and F. Well, if we call this now an artificial timetable by putting all these 7 lessons together, how many artificial timetables are there now? Obviously 7 factorial. What is the relation between the artificial timetables and the real timetables? Or in other words, how many different artificial timetables correspond to one real timetable? So here we have an example. This would be one real timetable, and this would be in the artificial timetables, for example, this one. So the first M here is a M1, the second M is the M2, and the third one is an M3. The first D is D1, the second D is D2. Then also corresponding to the same real timetable would be if we had here still M1, but just switch the D2 and the D1 here. Or we get another timetable, we keep the D1 and D2 as we had it in the first example here, but we just switch the M2 and the M3. So this is another artificial timetable. Or we could also just do both the switches, so the M2 and the M3 have been switched, and D2 and D1 have been switched compared to this one, and so on and so on. Well, this means that I can arrange the M1, M2, M3 in 3 factorial ways once the positions of the 3M is given. And the same is for the 2Ds. I can arrange them in 2 factorial ways. So 3 factorial times 2 factorial artificial timetables correspond to one real timetable. And for the French and for the English, there is only one of each of these lessons. Well, I can artificially expand this now by times 1 factorial times 1 factorial. So we have the same structure. You can write it there or not. Which leads us now to the number of timetables, which is the number of artificial timetables divided by the number of artificial timetables per one real timetable. And this is, in our example, 7 factorial, that's the number of artificial timetables, divided by this 3 factorial times 2 factorial times 1 factorial times 1 factorial. So generalized, this means we have k different elements, and of these different elements, the first element occurs n1 times, the second one n2 times, and so on, nk times the kth element. So summing up the different numbers of which how often each of the element occurs, we get in total, we call that n. So when we want now to look at the number of possible arrangements of these n elements, we find now n factorial divided by n1 factorial times n2 factorial and so on times nk factorial. So in the end, we just do the normal permutation formula n factorial, and then we divide by the number of repetitions of each of the elements. In the timetable example, we have 7 elements, and 1 being the number of math elements is 3, and 2 being the number of German elements is 2, and 3 being the number of English elements is 1, and then 4 being the number of French elements is 1 as well. And now when we insert it in here, we get 7 factorial divided by 3 factorial times 2 factorial and times 1 factorial times 1 factorial, so exactly what we saw up here. Let us now use our findings to solve example 2. We have a class consisting of 20 students, and the class has to build a football, a basketball, a hockey, and a tennis team, and they consist of 5, 6, and 3 members respectively, and no student is allowed to participate in more than one team. In how many different ways can the students be distributed to the 4 teams? That's the question A. Let us enumerate the students as 1 to 20, and now what team they are assigned to. So for example, student 1 plays football, student 2 plays football as well, student 3 plays tennis, and student 20 in the end has to play basketball. Well, we see we'll have here 5 times F, 6 times B, 6 times H for hockey, and 3 times T for tennis. Every arrangement of these 20 letters corresponds exactly to one distribution of the 20 students to the 4 teams. So this means that the number of distributions to the teams is equal to the number of arrangements of the 5F, 6B, 6H, and 3T. These are in total 20 letters, so it's 20 factorial divided by the 5 factorial times 6 factorial times 6 factorial times 3 factorial. And that's the final result. Well, what would be the result? We're looking at B now. If there was no tennis team and all the rest would stay the same, think about it for a moment. How many different distributions to the 3 teams would now be possible? Well, the result is exactly the same. Why is this the case? Well, we have now 3 students that will not participate. They sort of build a team of non-players. And well, that's the same like the 3 that before would play tennis. So whether they play tennis or they don't play at all, it makes no difference for the total number of distributions. Let us now look additionally at an alternative how to find the result in A. We could just say, in how many ways can I choose out of the 20 students the 5 that play football, where obviously that's 20, choose 5. Then I have to choose those that play basketball. Since I have already chosen 5 out of the 20, only 15 are remaining. So I get 15, choose 6, and I have to multiply the 2. Then 9 students are remaining, out of which I will choose the 6 that play hockey. And just for completion, right, well, there are 3 remaining, and I'll choose out of the 3 to play tennis. Since the 3 to 3 is 1, I could leave it away. Let us quickly prove that this is the same like the previous result. Well, 20 choose 5 is 20 factorial divided by 5 factorial times 15 factorial times 15 factorial divided by 6 factorial times 9 factorial times 9 factorial divided by 6 factorial times 3 factorial. Now we can cancel out. The 15 factorial here cancels out with the 15 factorial here, and the 9 factorial with the 9 factorial here. So what remains is 20 factorial in the numerator and 5 factorial times 6 factorial times 6 factorial times 3 factorial in the denominator. And we see that's exactly the same as we had before. So this shows that especially in combinatorics, like in many things in math, but really especially in combinatorics, we can look at the same problem in many different ways and get the same result by different approaches. So this is one part of the combinatorics. Just look at it the way that suits you and then find the corresponding result, as long as the way of looking at it is correct and suitable.